Everyone believed the sun's corona was simply hot. A halo of fire, blinding and uniform, the outer skin of a star too violent to ever touch. We were wrong. On December 14th, 2021, a spacecraft the size of a small car flew directly into that halo and lived. The Parker Solar Probe, built at the Johns Hopkins Applied Physics Laboratory, crossed a boundary scientists had drawn on paper for 60 years, and discovered the boundary wasn't where anyone had drawn it. What it brought back wasn't just data. It was a correction to one of the oldest puzzles in solar physics, and the answer was stranger than the question. Before that flight, the model was simple, almost comforting. The sun has a surface, the photosynthetic glow we see from Earth, roughly 5,400 degrees Celsius. Above it sits the corona, the wispy crown visible during a total eclipse. And for decades, the assumption was that the corona should be cooler than the surface beneath it, the way the air above a campfire is cooler the farther you drift from the flame. Stand close to a bonfire and the heat fades as you step back. That was the intuition. That was the textbook. Move away from the source, lose the heat. Except the corona is not cooler. It is hundreds of times hotter. The surface sits at a few thousand degrees. The corona, millions of degrees above it, burns at over 1,000,000 degrees Celsius, sometimes spiking past 2,000,000. Imagine walking away from a fireplace and the room behind you ignites into something closer to the surface of another star entirely. That contradiction sat unresolved in solar physics for over 80 years, ever since a Swedish astronomer named Bengt Edlund identified the spectral lines in 1941 that proved the corona's iron atoms had been stripped of electrons by heat no one could explain. That was the first crack. One number that refused to fit the model. And for 8 decades, nobody could get close enough to find out why. Parker Solar Probe was built to get close. Closer than any human-made object in history. Named for physicist Eugene Parker, who in 1958 predicted the existence of solar wind when most of his colleagues thought he was wrong, the spacecraft launched in August 2018, carrying a carbon composite heat shield 4.5 inches thick, designed to face temperatures exceeding 1,400 degrees Celsius, while the instruments tucked behind it stayed close to room temperature. The descent began the moment it crossed into the corona itself, and the layers it passed through told a different story at every level. At the outer edge of the corona, the temperature is brutal, but the density is almost nothing, thinner than the best vacuum humans can manufacture in a laboratory on Earth. You could survive the heat for a fraction of a second if the radiation didn't kill you first, because there's almost nothing there to carry that heat into your body. Heat without substance. Fire with no fuel. Deeper in, the probe began detecting something nobody fully expected. Magnetic switchbacks. Sudden zigzagging reversals in the sun's magnetic field that snap backward like a whip cracking, then straighten out again seconds later. Dr. Stuart Bale, a physicist at the University of California, Berkeley, who led one of the probe's key instrument teams, had spent years modeling the solar wind from a distance. When the switchback data came back, he didn't hedge. He put it as bluntly as a scientist ever does. He said the sun was sending out something closer to a series of explosions than a steady breeze, and that the old picture of a smooth, outflowing wind was simply wrong. Not everyone agreed on what was causing it. Dr. Justin Casper of the University of Michigan, who had spent his career studying solar wind acceleration, argued the switchbacks were the visible signature of magnetic reconnection happening deep at the base of the corona, energy released in violent snaps as magnetic field lines broke and reconnected. Bale's team leaned toward a different mechanism, turbulent waves rippling up from below and twisting the magnetic field as they rose. Two brilliant teams, looking at the same readings, reaching different conclusions, and neither willing to concede. The disagreement wasn't a failure. It was a signal that the corona was more dynamic, more violent, and less understood than anyone had let themselves believe. Then, in 2021, a paper published in the Astrophysical Journal confirmed the spacecraft had crossed the Alfvén critical surface, the theoretical boundary where the sun's magnetic field stops dominating the solar wind and the wind breaks free into space. Researchers who had spent careers building models that placed this boundary at a fixed, predictable distance had to ask whether the foundation itself was sound. Because Parker found that boundary wrinkled, uneven, folded in on itself like a coastline rather than a smooth sphere. The sun didn't have a clean edge. It had a frontier that bent and buckled depending on what was happening beneath it. Inside Mission Control at the Applied Physics Laboratory, when the first telemetry confirmed the spacecraft had survived its closest approach, systems engineer Nick Pinkeen later described the room going quiet in a way that had nothing to do with relief. He said it felt like watching something come back from a place that wasn't supposed to send anything back at all. He struggled to find better words for it than that, and his struggle said more than a polished sentence ever could. What the probe found at its closest layers was both the most violent and the most exquisite thing connected to our star. Inside the corona, gas moves so fast and so randomly that it generates plasma waves singing at frequencies the instruments converted into sound. An eerie, looping whistle that scientists nicknamed the sound of the sun breathing, recorded inside a region hot enough to vaporize steel in an instant. Beauty and annihilation occupying the exact same coordinates, the exact same second, the exact same breath of solar wind. A storm of charged particles, capable of stripping the paint off a spacecraft, also produces light patterns more intricate than anything visible from Earth. Patterns no human eye will ever witness directly, because no human eye could survive being there to see them. This isn't only a curiosity for astrophysicists in conference rooms. The solar wind Parker is mapping is the same wind that triggers geomagnetic storms capable of knocking out power grids and disabling satellites. The same activity that forced a partial blackout across Quebec in 1989 and threatens the global positioning, banking, and communication infrastructure an entire civilization now depends on. Space agencies planning crewed missions to the Moon and eventually Mars are using Parker's data to model radiation exposure windows, because a solar storm during a months-long transit to Mars could be lethal to a crew with no magnetosphere to hide behind. Nations now treat solar weather forecasting the way they once treated ordinary meteorology. An early warning system that didn't exist in any reliable form until a spacecraft flew close enough to the fire to finally understand how it actually burns. Step back from the data, from the switchbacks and the Alfvén surface and the singing plasma, and consider what it means that a piece of human engineering, smaller than a delivery van, flew directly into the atmosphere of the star that makes every living thing on this planet possible, and came back able to tell us we had been wrong about it for 80 years. There is something quietly humbling in that. We built our understanding of the nearest star from 93 million miles away, through filtered light and careful inference, and we were confident in that understanding, the way you're confident about a room you've only ever seen through a closed window. Then something finally opened the door, and the room was on fire in a way the window had never shown. You have spent your whole life standing under a sun you understood, a steady yellow disk that rises and sets and asks nothing of you. It was never steady. It has been screaming this entire time, in switchbacks and waves and reconnections too violent and too fast for any unaided eye to catch. And the only reason you didn't know is that nothing had ever gotten close enough to listen. Now you know. And you won't be able to look up at it quite the same way again.